These are the solutions for the astronomy practice quiz. Not all questions on the practice quiz will be on the real quiz. As always, if the background of a slide is blue, it's not required. The first question was to explain the difference between the geocentric and heliocentric models. This is covered on this lesson right here down below. So if you're watching this, you can pause the slideshow, look at the real assignment, and just click on these links. Both of these try to explain the motion of the planets we see in the sky. So that's what's similar about them. But the geocentric puts Earth in the center of the solar system. Heliocentric puts the sun. There we go. All right. I'm just not going to redo this. Okay. The biggest problem was this Earth-centered one had trouble explaining retrograde motion. That is, when the planets are going around, they seem to go backwards briefly. The sun-centered had no problem explaining that. If Earth is going around the sun nice and slow, Mercury here is just going zing, zing, zing around. So for a while, Mercury is gaining on Earth from behind, right? And then as it goes this way, we see it going, oh, it's coming up at us, and then suddenly it's going backwards. Then it's coming forward, going backwards. It's dead easy to explain. Still doesn't make it true, right? The main difference, the two models, this one was more complicated than the other one. And in the lack of any other evidence, you should probably focus on the simpler one. But it had to be observed to see it. But that's the basic difference between the two. Now, the other thing the heliocentric model could do is predict the seasons. This is something you need to watch. The textbook does a terrible job on this diagram. It makes it look like you're staring at it from above. So I've put a 3D effect in here. Notice the arrow. This Earth position here is behind the sun. This is in front, to the left, and to the right. This little tilt here, this long line is the Earth spinning on its axis. The sun is only going to light half the Earth at a time, but because the Earth is spinning on a tilt, someone down here in the Antarctic Circle, the spin will never take you out of sunlight. But up here, you're always in darkness. And as we turn on this axle, the people north of the equator spend more time in the shadow than in the sunlight, while these guys down here are spending more time in the sunlight than the shadow. So this is summer for the south, winter for the north. Over here, it's the opposite. The top of the Earth is tilted to the sun, the bottom tilted away, so now we have summer and winter. At this position in the front and this position at the rear, the Earth's tilt doesn't affect the lighting because the tilt is sideways to the sun. So no matter how it turns on this axle here, it's going to get 50-50. So at this point in time, we wind up with a 12-hour day, 12-hour night. So it's spring or summer. Now, which one is it? Well, think about it. If we're in winter right now and the Earth comes this way, it's our spring. But if you're down here in Australia and it's summertime, this is your fall. Okay? And putting the Earth in the center of the solar system, this just doesn't work out that easily. So our tilt causes the seasons. Now, when we looked at this, one of the things, and this is not testable, the slide is blue. How would you explain in the history of science the great breakthroughs of advancement have always been the work of a single person? Well, it's patently false. Hollywood loves the idea that one person changed the world. And some, like Einstein, he was just like right out of the blue. There were some other people working towards him, but he was one of the few, him and Newton, that were just really like, yeah, they did something nobody else did. But if we look at our understanding of the solar system, the people we know of, there could be more, was the model was proposed by Copernicus. Tycho modified the orbit to ellipses because it fit the data better that Tycho got from the real universe. So theory, modified theory because of observations, and Galileo made an instrument that allowed him to observe the fact that there were objects rotating around other things. And Newton was able to give the reason why, a mathematical theory of gravity that explained it. So this took at least 5 people in more than a century. And it spans all the way from almost the equator right up into near the Arctic Circle. So no, science is rarely the work of a single person. When we get to comets, again, there are simulations you can watch. But the main thing about a comet is its ice. So as it approaches the sun, it starts to melt. And the sun has radiation winds blowing away from it. So the comet's tail always points away from the sun. And with every visit, the comet shrinks. And eventually the comet completely evaporates, and all that's left behind is a boulder field in space, little pellets and gravel and dirt. And so we get meteor showers instead of a comet from that point on. Now, the danger that comet represents is the asteroid belt is way out here orbiting between Mars and Jupiter, and it obeys the rules of the solar system on the flat. But comets go way up and down on this severe angle, tilted out of the plane of the orbit. So fortunately, it is tilted. If these comets came straight in, dive bomb across the orbits, there'd be a huge collision risk with Earth. As it is now, when the comet comes screaming down through the orbits of the planets, their intersection risk is a little bit lower. Asteroids should be safe because they're way out here. They do get ejected from their orbits occasionally. So the difference would be that there are only 4,000 known comets, and there have been millions of asteroids. So even though the asteroids one at a time are individually a lower risk, in group, they're very dangerous. Now, what is Uranus's distance in astronomical units? You did it in this assignment. You're simply going to take the Earth-Sun distance, the Uranus-Sun distance, and divide the two. Since both have 6 zeros, doesn't matter. We get 19. Therefore, Uranus is 19 astronomical units from the sun, 19 times further from the sun than we are. There's a whole assignment on this. How long does a beam of light take to get to Mars? This should be a blue slide. Okay, it's not on tomorrow's quiz, so I will leave it be. Skip this one as well. It's not going to be on the quiz. Scale model problem. This is a guarantee. You did this with the Giant. Andre the Giant is on the cover of this assignment. You did a whole scale diagram. Now you're just doing it with the planets. It's ridiculously easy. You can simply take the one planet side divided by Earth's side, and you get 9. Saturn is 9 times bigger than Earth. The advanced part is this. And I would like you to be able to do this, but not on the quiz and not on the unit test. Okay? But I would like you to read this over and get an understanding of how this works, but you will not be tested on it. So if you're overwhelmed with this part, totally ignore this part. Okay? And that's the review.